about to get started. Let me get the live stream going. Great. So welcome back, everyone. We're going to be talking, we're going to finish talking about locality-sensitive hashing. So today is an extension of min hashing. I'll try and explain a bit more how you would actually turn this into a data structure and give you a couple of other examples beyond the min hashing example, which is kind of the first powerful one, but then we'll see Jacquard and Euclidean distance, or at least versions of them. And then I'll talk a little bit about some distribution distances where what you're comparing is not just a vector, or maybe, but it's a set of points, or it's a set of objects, or maybe a continuous distribution, kind of a multi-dimensional space. How would you compare two data sets to each other? So we'll talk a little bit about that, depending on how far we get. Last time I taught the course, I had a whole lecture on that, and it's kind of maybe technical dry when I gave the lecture. Students' faces were not too excited, so we're not going to do a whole lecture on that today. But I've got some nice ripened notes on it for the stuff we don't get to for those who are interested. Okay, just some bookkeeping before we get started. I brought some example posters up front. Please look through them. I carried them halfway across campus, and I'll have to carry them back afterwards. Again, I can't post these online because of some FERPA rules and so forth. They have names on them, as they should. But you're welcome to look at them and get ideas for your project. Let's see, your project proposal is due today at the end of the day. So we will, I will, it's again only 100 to 200 words, basically who's in your group and what you're planning to work on. I will look at those and kind of give some feedback if needed on those to make sure the project sounds like in the right ballpark. If I don't tell you something too specific, that means that it should be basically fine for now. You're welcome to modify and change the project. If you do, you might want to send me a note or come talk to me just to make sure it's still something that sounds good. But I want you to get thinking about this sort of stuff. Okay, great. And then the first homework, I believe we had all the grades posted on Canvas. Is that right? That the first homework, those come back. There are regrades requests. Those are through Gradescope, and I believe that Elisa, the TA, will get notification and look at them as needed. Okay, and then a reminder, the second homework on similarity search is due in a week. So the first two topics, we should have covered what we're going to cover on them in lecture already. And again, a reminder to get started on 2A. It might take a little time. Who's got some nearest neighbor search kind of thing installed so far? Okay. Okay. Great. Is there a question? Oh, you weren't able to install Kgraph. That was hard. Okay. All right. It doesn't matter which one you use. I just want you to get used to it. The Kgraph one is not as optimized. This one I had gotten installed. That was the first one I ever used, like of this family of things, like 6 or 7 years ago. It may have been out. Yeah. Okay. If you have only out-of-date Python installed on your laptop, like I probably do, then that one might be better. Otherwise, some of the FAISS space or DiskNN or any other one you find online that you think is easy to install that will demonstrate this is fine. This is kind of a powerful new tool I want you to explore with, and there are a lot of options out there. It's kind of a research active topic. There are a bunch of people installing. So maybe the Kgraph one is not good if you are more up to date on your Python than I am. Um, oh, okay. Good. Well, okay. So just I've warned you. I don't hope it's onerous or takes too much time, but that's where there's some uncertainty for me. Okay. And then okay, and then this is the last topic on similarity search. We're talking about distances, similarities this week, and how to search and process them quickly. We'll move on to a new topic on clustering starting next week. Okay. So kind of all your questions about similarity search are on topic to ask now, but this will be super relevant for kind of the core building block of everything else we'll talk about in the semester. Uh, okay, so let's talk about some locality-sensitive hashing. And as a review, last week we talked about min hashing. Okay, and so this was you could draw a hash function from a set, and we described how to do that from a family of hash functions. And we described how to do that algorithm last lecture. And this has the property that the probability over the choice of the hash function, which depends on your kind of your salt, you put in some other H prime hash function, that I have two sets. So S1 and S prime and S prime are sets. We talked about how to get these sets as k-grams of these documents. The probability that the hash value of these two sets is equal is going to be exactly the Jacquard similarity between the two sets. And we talked about that also on Monday. This was the size of the intersection divided by the size of the union of the two sets, right? So it was nice. It didn't depend on the universe it came from. That meant if we saw new k-grams for some weird new text, some new slang on Twitter, then it still works. We don't have to re-engineer all of our tokens in order to handle that. Okay, so this also implies that this is equal to the expected value, again, over this, of that these are going to be equal, right? So they're because they're either equal, we get a 1, or it's I should write this as, actually, let me write this slightly differently here. The expected value over this choice of the hash function that I get a 1. This is an indicator function. It's a 1 if they are equal, 0 if they're not equal, right? This is also equal to the Jacquard similarity. Okay, so I can get the right expected value by assigning a 1 if they're equal and 0 if they're not equal. If they're completely the same, it's always 1. If they're completely different, it's always 0. If they're the overlap, if the Jacquard similarity is 1/3, then the expected value of them being equal is 1, and the expected value of them being not equal is 0. So the expected value of them being equal is 1/3, right? So the expected value I get a 1 is 1/3. Expected value I get a 0 is 2/3, but 1/3 times 1 plus 0 times 2/3 is 1/3, right? So I get the right Jacquard similarity again here. What this means is that I can actually draw H1, H2 up to HT, say IID, from my family of hash functions. And now I can create the Jacquard similarity approximation between S and S1 is going to be equal to 1 over T times sum over J equals 1 to T of a 1 if the hash function Js equals hash function J of S prime. Okay, so I can create this approximate Jacquard similarity by taking a bunch of hash functions and counting how many times they intersect. All right, I'm measuring how many times they intersect. I get a 1, this indicator function, right? This is 1 if true and 0 if false, right? So that's what the indicator function is, and that's true if they're equal, right? So I'm counting how many times are they the same. Yeah. Well, okay, so the min hashing is, the result is I hash every single element and I take the minimum. When I return that minimum, that is H. H prime was hashing an individual thing, but H is this min hash function. Okay, I'm not redescribing how it works in this lecture. Yeah, other than what I just did. Okay, so this is an average of all these hash functions. And so by linearity of expectation, the expected value of H1 up through HT of the Jacquard similarity between S and S prime, right, of the approximate Jacquard similarity, well, this will also be exactly the Jacquard similarity between the two sets, right? So I'm getting an so this is still approximately right, but if I take a more average over more and more things, it's going to concentrate, right? And you can argue that as I get more and more, I'm going to get a better and better approximation. Okay, so to get a signature for a single set, I'm going to create a set of T hash functions, and I'm going to kind of stack them inside some vector. And then I'm going to take the L0 distance between them, or I'm going to count how many times they're similar, or average how many times they match exactly, right? And that's going to be my approximate Jacquard similarity. Okay, so this is another way I can compute the approximate Jacquard similarity. If the sets are really big, like billions of tokens, and I use T equals 1,000 and I pre-process, maybe this is a little faster, but this yet is not the main point of locality-sensitive hashing. Okay, I haven't turned this into a fast algorithm yet by doing this. This is just to illustrate that I'm going to create a signature of a bunch of these hash functions. And I want to combine them together to estimate if things are close or not close. Okay, so this again, so this is not giving me really much useful speed yet. Instead, I'm like, what I want to look at is that a picture here where I'm going to label this axis S and think of it as the Jacquard similarity between two sets. Well, I have big S and little s here. So let me. Okay, so small s is the Jacquard similarity between the two sets. Okay, and I want to say the probability that H1, that for H, draw it from the hash function, that H of S is equal H of S prime. And again, I'm just looking at a single hash function. And what I know from the min hashing is that the similarity is going to go from 0 to 1 between the two sets. And also the probability they're going to intersect is going to go from 0 to 1. And I'm going to get a line that looks like this. Okay, so the probability that they are going to collide is going to be exactly equal to the Jacquard similarity. And so if I do one hash function, I get a line here. And I want to make an observation and estimate what the Jacquard similarity is. Now, what I actually want to do is I want to check are they very similar or not? I care about the nearest neighbors. I don't care about if something is kind of a median neighbor, I can be off by a bit. I don't care so much. I kind of want to pick a threshold that I think means that they're very similar to each other. Let's say 0.7. Often 0.7 would means things should be maybe very close. Now, I might need to change this later, but I would like a different function instead that's going to look something like this, okay? Where if the Jaccard similarity is above 0.7, I'm going to have a very high probability that things are going to collide. And if it's below 0.7, then it has a low probability that these are going to collide. In fact, what I would really like to do is some step function where it went like this. Things only collide if it's above this, and this is kind of ideal, but I'm going to get something like the red curve with LSH. Okay, and this is one hash function. Okay, one hash function, I can get a value, but it's really only going to give me 0 or 1. I want to say that I'm going to have collision really only if it's above some threshold. Okay, and I'm not going to be able to get it exactly the orange curve, but I'm going to get it kind of close. I'm going to transform, instead of one hash function, my set of hash functions into something like this red curve. And I want to be able to answer this quickly. Okay, hash functions are nice. I can check, how do I check if two things collide in a hash function? If I have a query and I want to see if anything else in my data set collided with that in one hash function. Yeah, I store it in some hash table or some hash or some set data structure, right? And I look at all the things that map to the same object in the set data structure or the hash table. And those are things which collide. I store them and then I can read them off, right? It should take constant time, right? There's some minor overhead in here if you really look in the details, but it's roughly constant time. I can look at a cell and list all the things that hashed into that cell. They're the same, and I hash my query into a cell and I look up everything that hashed in that other thing. So I can do that really fast. So I want to find all the things which are similar above a threshold. I want to just read them off from the hash table cell. Okay, but if I have one hash table, well, if it's probability 0.8, well, I'll look in there and some stuff in the same cell, things that are, if they're above 0.8, well, 80% of the time they'll have collided, and sometimes they won't collide. And sometimes other stuff will collide in there that shouldn't have collided. Okay, so that's not quite very helpful. So what can I do? What can I do to kind of combine these together in a smart way? There are kind of two options I can do, and I'll need to do both of them. How can I leverage two hash functions? So what if I wanted to be very aggressive and not worry about false positives, but I don't want to miss any false negatives? If I have a bunch of hash functions, what should I do? I put my query into all the hash functions, right? So I want to be aggressive. So few false negatives. Okay. So what I would do, I would put query Q into H1 of Q, H2 of Q, of HT of Q. And I look at, for each of these, it's going to have a list of the intersection. Right? So I'm going to have a list of things which are intersect with the cell. So a list of all the things that intersect in the same cell in the hash table as Q, right? And so if I don't want to miss anything that could be close, I can look at all these lists. So I can take the union, right? So I can take the union of all intersections. Okay, so how fast can I do it? Well, proportional to the size of the intersection, right? So I just read off, I hash into the cell in the hash table, I read off everything. The next one takes constant time to hash here, I read off everything. So it takes as long as the number of intersections. So if I have too many intersections, it's going to take too long. But if I really want to report all these things, then it's as long as it takes to actually read all the things I'm reporting. So that's okay. But there's going to be some false positives in here as well. Okay, so this is the aggressive way of doing it. I want to report anything that might be similar. What if I want to go the opposite direction? This one's a little bit trickier. What if I want it to be conservative? So I want a few false positives. Okay, so I don't want to report many things, hopefully nothing, but not many things that are not similar. So how would I combine together the hash functions? I can't use T different hash tables anymore. I need to do something a little bit more clever. Okay, what I'm going to do is I'm going to concatenate H1 Q, H2 Q to HT of Q, and put this in a big hash table, right? So there's going to be another hash function that stores this concatenated values, okay? I make each of them the same length, so there aren't any kind of collisions because this is length 1, this is length 2. Like 1 and 12, I don't want to look like 11 and 2, so I make it 0, 1, and 1, 2, but I concatenate them into a unique hash as a combination of all the hashes, right? And now this stores one hash table, and it's going to have one list here. So I'm basically taking the intersection of all of the hash tables. I only return something if it's in the intersection, but I can use one big hash table to do this so it's efficient. I can pre-process for all of my data, pre-process it by applying all these T hash tables, map them into these really big kind of cells that are very specific. It only is in there if it lines on all T of the hash tables, and then I report what's in here. Okay, so this will have very few false positives, right? Things that I say they're similar, but they really aren't. So it would have to be a big surprise for it to match on all the hash functions, even if they were fairly different from each other. Okay, but this one is too aggressive, this one's too conservative. I need to somehow do something in between. Okay, and so the trick is to do something called banding. Okay, so I'm going to have these hash tables H1, H2, H3, H4, up to HT, right? And so what I'm going to do is I'm going to group some of them into a band. Well, I'm going to turn this into, this will be H1, this will be H2, and this will be HT over 2. Okay, so I'm going to concatenate the results of these two things and put them into a big hash table. And then I'm going to take the union over these T over 2 hash tables. Or if I do this if I make it bigger, if I have bands of size B, right? If I have this, let me see if I can get the notation to match. Well, okay, I may have let's say I have bands of size B. So instead, this is H1 up to HB. This is HB plus 1 up to H2B and so forth. HT minus B up to HT. Right? So I can variably I can choose how many things to put in one band and then how many bands I have. Okay, and so I need to have that the total number of hashes. This is the total num of the hashes is going to be equal to B, the size of the band. This is the size of the band times R. This is going to be the number of the bands. So this would be 1, 2, T over B is equal to R. Okay? And so then I'm going to take the union, return the union of the collisions on these super hash tables H1, H2 up to HT over B. Okay? So this is the idea. And so each one, if I store them as hash tables, I can look up everything in the intersection set in as constant time plus the size of the intersection, and I just report out everything. I may need to remove duplicates, but not a big challenge. Okay, so let's have a little bit of a picture of how this works. If I find a collision, so I've taken the similarity now and I've plotted it on the x-axis, this is S, and the y-axis is the probability of collision. And so I've taken the similarity, and in order for it to not show up, it has to, for it to not collide, it needs to not collide B times independently. So that's S to the B. And then 1 minus that is the probability it does show up in one of the hash tables. And then R is the probability I have R chances to do it. So it's that to the power R. And so I get this curve that looks like this. And as I increase, this is with 15 total hash tables. This means that hash functions. So 5 hash tables, but I get B times R equals 3 times 5 equals 15. So I have 15 total hash functions. I get a curve that looks a bit like this, right? So if I increase the number of things, the number of bands, right? I think this number of bands, it should, if I get this correct, okay, so it should, the number of bands should give me, I have more chances to get it, so I should have a higher probability of seeing a collision, right? So I have a higher probability of seeing a collision. So if I went from a curve here and I increase R from 5 to 15, how should this curve shift? What should the effect be on the curve? So if I have a higher probability of seeing a collision, the y-axis, the probability of a found collision, what should happen to the curve? Should move to the left and up. Okay, so it should be moving a little bit to the left and up before, right? This was B equals 3, R equals 5. And so I've moved to the up and left. That means because I have more chances to hit, a smaller similarity thing now has a high probability of being collision, where before it was a small probability. And if I add more bands, or the size of a band gets bigger, so if I have more things in a band, what should happen? It should move the other direction a little bit. Okay, now if I change the number of things in a band to 6, now it's moved back a little bit. Okay, again, the total number of hash functions is now 6 times 15. So I've had to use more hash functions. So this is going to be 90 hash functions instead of only 15 before. But now I have 90 hash functions, and the curve, okay, it's the similarity where the threshold is about 0.6 again, but the curve should be steeper. If I put these all on the same, if I move the band number size of a band to 10, it moves even further this way and becomes even steeper, right? So if I, and this is now the size of the band is 8 and the number of bands is 100. Okay, so the kind of threshold is maybe 0.55 with this choice, and it's become quite steep, kind of like what I promised with that red curve, right? And so here's a bunch of stuff together, right? You can see the black curve is with b equals 3 and r equals 5, right? So this was b equals 3, r equals 5 is this one. And the red one is going to be b equals 8, r equals 100. And so it's much steeper. I'm getting a better differentiation. If it's above 0.7, I almost always find it. And if it's below 0.3, I almost never find it. And in this range in between, I sometimes find it. I get false positives and false negatives. But not if it's very dissimilar or very similar. Those I get almost always. Okay, so there's some zone in here, right? There's some zone still in this region, right, where I'm not sure. Right, so this zone, I get kind of a maybe collision. I get yes and no in these zones here, right? So I get, and as I get more and more hash functions and tables, it takes a little bit longer. I have to look for r equals 100. I have to look in each of those individually to report everything in. So I have to spend time proportional to r. The time proportional to b is kind of in the pre-processing. Okay, and I can balance r and b to kind of move this, keep it steep, but move it kind of back and forth a little bit. Okay, so there's kind of some weird stuff to get all this to work, but this is kind of the big picture here. Okay, hopefully you kind of get a sense of how to do this. It's a little bit complicated. This is actually not the optimal way to use the hash functions. There are data-dependent ways where they choose when to employ them, structured by the data, and those give slightly improved bounds in theory and in practice. And in fact, people have shown upper and lower bounds asymptotically on how fast you can do nearest neighbor search in high dimensions, and these match the optimal possible bounds. You can't do better than this LSH sort of strategy with some data adaptive way. They're probabilistic, but like you might need to spend, and it's something like to get a factor 2 approximation in the Euclidean distance. I'll tell you how to do Euclidean distance LSH function in a bit. I need to make this something like n to the 1/7. Okay, and again, n to the 1/7, O of n to the 1/7, but people have engineered these, but they don't beat these graph-based methods. So I've moved that part of the lecture up in the semester. Okay, you kind of get the big picture of how this works. Maybe you kind of, I'm not going to ask you to implement this year, and the details on how this works, I think, are not super important because you're going to use someone else's code to actually do this anyways. Okay, but I want to kind of reveal some of the mystery of how you put together these locality-sensitive hash functions. And hopefully this has revealed some of the mystery. That makes sense? Okay, still kind of mysterious. Okay, well, it would go on a lot longer to reveal everything under the hood. Okay. Okay. So I want to. Okay, so I want to talk about a couple of other ways you can do locality sensitive hashing, just to show you the variety of approaches this can be used for. And we're not going to spend, I hope not to spend too long on this. Again, just give you a high level picture of these ideas and not go through all the detail. But I'm going to talk about one that actually works really well, is super simple to use, and corresponds with the cosine similarity. Okay, remember the cosine similarity? I have two vectors, A and B, and the cosine similarity between sim cosine between A and B was going to be the is the dot product between A and B. This is assuming A and B are on SD minus 1, right? So they've been normalized, and I've drawn them on the unit circle, so they're on S1. Okay. Okay, the cosine similarity is not 1 minus that is the cosine distance, and that is not a metric. I said instead that there's this the angular distance instead. And we're going to talk about the angular distance, which you can, or the angular similarity. And remember that the S angular of A and B is going to be the arc cosine of the inner product between A and B. Okay, so I'm just taking the arc cosine of this. So it's kind of it's a monotone operation. And what that tells me is now the similarity is 1 minus the distance between, or this is, no, the arc cosine, and it's 1 minus the arc cosine, right? It's a little, yeah, the arc cosine is weird. Okay, so it's 1 minus, the distance is 1 minus the arc cosine. This gives me the angular distance in radians, okay, in between here. And so this is a metric because it's the shortest path on the circle. And that's true on any hypersphere. Okay, it gives me the short path as long as I walk on this manifold. So it's a geodesic distance, which turns out will make it a metric distance. And it's nice. Okay, and I'm going to actually work with something called S angular of A and B, which is going to be equal to the similarity between A and B, the angular similarity here. What am I doing? Why is this not working? Okay. The angular similarity divided by pi. Okay, so now this value is going to be in 0 and 1, like we talked about. Okay, so all I did by dividing by pi, the biggest distance I could be from 2 points is when they're opposite sides of the circle, then the distance on a half circle is pi. And that's true in a hypersphere as well. If they're two antipodal points, the shortest path is along the great circle that passes from one to the other. And if they're antipodal, it's still a distance pi. So if I divide by pi, then the distances and the similarities in 0 and 1. 1 is if they are exactly the same, and 0 is if they are antipodal to each other. Okay, and again, I want to do this because I'm going to do a hash function where the probability of the hashes colliding is going to be exactly this normalized angular similarity between them, which I can map back to the cosine distance through this simple transformation. So I can go back to it if I want. Okay, but I'm going to work with this normalized angular similarity. Okay, and so now I need to come up with a hash function. Okay, this will be kind of it's different. I can't use like a min hash trick anymore. I need to use a different trick. Okay, so the angular, let me draw this picture again. We'll have A, B, and now I'm going to have an angular similarity hash function. Question? Well, this is a similarity, not a distance, right? So remember the last lecture we talked about the difference between, and the similarity inverts the similar things have large values, and so have a high similarity. That means 1. Low similarity means 0. And so with LSH, it's easier to talk about similarities. And with all these, you do the 1 minus trick to convert between them. Okay. Well, it depends what you want to convert between, but okay. So in this case, you get a metric distance by doing the 1 minus trick once you're in this range. Okay. Okay, so how do I get a kind of a hash function? And the trick, I'm going to get a hash function h of u between a and I'm going to want to know if h of u is equal to b. And my hash h of u is going to go from d minus 1 to only going to hash to 2 items, -1 and +1. It's going to hash to only 2 bins. So it's a very simple hash function. And it's going to depend on u, which is going to be also a vector in SD minus 1. Okay, and the hash function, so h of u of a is going to be the sine of the inner product with a with u. Okay, why does this make sense? If I pick a vector u, well, the sign is the same, right? Everything on this side of this normal direction to u, right? I define this kind of half space, and everything on this side of the half space has a positive sign. Everything on the other side has a negative sign. So I've divided it equally and randomly by picking a random direction. Okay, so these A and B now have the same sign. The more similar they are, the more likely they are to have the same sign. I can only get something with a different sign if I if I move my u down, u prime down to here. Now the normal is going to split A and B, right? This one, which h u prime of A is not equal to h u prime of B, but for this one, they are going to be equal. The green one, they are equal. The orange one, they're not. There's only some very narrow, if they're similar, that means they're pointing in the same direction. Only a very narrow range of things are going to actually kind of separate these things. And even if I'm in high dimensions, the geometry of this still works. I can project everything onto the plane that go through 0, A, and B, and the same analysis and calculations work. Okay, so this is how I build the hash function for angular similarity and cosine similarity. The hash is 0, 1, but the probability of colliding is still exactly the similarity function. Right, so I just have to store a bunch of bits and see if the bits match, and then use the kind of the Hamming distance between the bits to approximate the cosine similarity. And I can plug it into the LSH framework with the banding and all that stuff. Okay, if you're paying really close attention and you didn't take my advanced class last fall, you might be wondering, how do I choose U? How do I choose my random salt? Now I need to be a little bit more careful. I need to choose the direction at random. And so how do I do that? How do I choose so I need, in fact, this to be uniform over the space of all unit vectors. I need U to be uniform over the space of all the unit vectors. How do I do that? How do I pick a uniform unit vector in high dimensions? All right. So the proposal is to generate a vector, let's say X, which is in uniform 0, let's say -1 to 1, times uniform -1 to 1. Right? So I want to generate a random vector X in this box and then set U equals to X over the norm of X. So I've normalized it, right? So so this is my box, and this is 0. This is -1 up to 1. I pick this point X, and then I normalize it by mapping it up onto the sphere. Okay, so this does not work. This is a good common guess, but this does not work for the reasons we talked a little bit about last week, where in 2 dimensions it works close enough. It's probably fine. But in high dimensions, these corners is where most of the volume is. So very high probability you're going to pick some point in the corner, the point inside the ball, and I push it out. If I get a point inside the ball and I push it out, it'll be uniform everywhere on the ball. But if I get a point in the corner, it's more likely to have a bunch of correlation between the values. Okay, good. Okay, what if I picked a normal distribution instead? Right, so what if I pick G from a normal distribution? Maybe a D to, and in fact, I can do times another normal distribution. So I picked all the coordinates of G from a D normal distributions. Is this going to work? And then I set U equals to G. Who thinks this one will work? Who thinks this one will not work? Who's uncertain? Okay, good. It's engagement. Okay, so this one actually works. So this is really cool. So this is the cool trick. This works. The normal distribution has this amazing property that it's the same in every direction. I can change the basis, and it's still a multi-dimensional normal distribution. I can generate the coordinates independently, and I get a high-dimensional Gaussian, which is a multi-dimensional normal distribution. I can generate coordinates independently, and then I normalize them, and it will be on the unit circle. So this works. So this is great. This works. I have to generate something from a single normal distribution, d times still. There's something called there's a way to do this, something called a box. Write a little bit better. Box Mueller transform, where I can take 2 uniform random values in 0, 1 and turn them into 2 normal random values that are uncorrelated. And so I do that d over 2 times, and I get d coordinates. If I have an odd number of coordinates, I can throw one away. Okay, but so this is how I do this, and I get a normal direction. This is a cool trick. Okay. Okay, so this is how we get these hash functions for angular similarity, which can map to cosine similarity through some kind of trig and algebraic transforms. Okay. Okay, how do we do Euclidean distance? Okay, with Euclidean distance, let's start locality sensitive hash for Euclidean. Okay, and let's start in R1. Okay, so now all my points lie on R1 dimension. We'll do one dimension at a time. And I'm going to tell you the trick. I'm going to tell you that this is my notion of my threshold for similarity. So part of the LSH, I want to only return things that are similar if they're this distance apart. I need to use this distance in the LSH for Euclidean distance. So I need to know what that is in order to have a good hash function. This one, I resolved what the threshold was through banding, right? This one always gave me something about 0.5, but I can put more things in a band versus number of bands in order to kind of resolve where that threshold was. Here, I need to use this similarity here. And so now I want to have a function. So if I have 2 points, A and B, I want to know what's the probability that they're going to hash together. I want that to be proportional to the similarity here. So I want to say, if they're less than this distance, the similarity is, I want to say, okay, so let's call this value sigma. I want to say that the probability that hash of A equals to hash of B is going to be equals to 1 minus the distance between A and B. And in R1, this is just an absolute value, divided by S, or this, sorry, sigma. And this is if A and B are going to, if this is going to be if A minus B is less than sigma and going to be equal to 0 otherwise. So I want the probability of collision to be 0 if they're further than sigma apart. Well, it turns out I can actually just draw this function on top of here and say the probability, I'm going to have 0 and 1, and the probability of colliding is going to be something like this, where this distance is sigma. So I get this triangle shape, okay? So this is kind of a triangle. I can think of this as a kernel, like a Gaussian kernel, but this is a triangle kernel. I can define it in this way. And so now I want a hash function for this. Well, in order to, this is my similarity function. It's 0 here, and this is a similarity associated with the Euclidean distance in 1D. And so all I do is now I'm going to put down some bins of length sigma. Okay, and if A and B fall in the same bin, then they're going to collide. Okay, they didn't fall in this same bin, they split. So I need to add a random, so S is determined, sigma is determined, but I'm going to have a random offset. Right, there's going to be some offset beta from 0, and this is the randomness. I choose this random offset, and then I just put down some bins, and I see if A and B fall in the same bin. And the probability they fall in the same bin will be exactly this similarity function, which is described by this triangle kernel. Okay, and so in one Euclidean LSH for Euclidean distance in 1D, it looks just like this. Okay, so let's quickly say LSH for RD Euclidean. Okay, so I'm going to kind of go through this pretty quickly, but I'm going to combine my hash function will now be depend on U beta. Okay. And what I'm going to do is I'm going to say that for A, it's going to be beta plus the inner product of A and U. And then I'm going to take the floor of this function. Okay, so what is this picture doing? I'm picking a random direction U. Okay, this is on a circle. Okay, and then I'm going to take an offset beta. I'm going to put down some bins. Maybe it's minus beta. That's not too important here. Maybe I'll put minus beta if you actually care. Okay, and so that minus beta. And so now my point A will fall in this bin, and it's going to get a value 1. Another point B will fall here. It's going to get a value 2 because it's in the second bin. Okay, and this will not give me this straight line. It'll give me something that is approximately what I want, but it's approximately if they're within some threshold of distance, they're going to be mapped to the same bin. And I'm going to try a whole bunch of these hash functions and use banding, and I can get it to work. Okay. There's more details under the hood, but this is the basic idea. Combine the two ideas from the cosine similarity and this one-dimensional, and you kind of put them together and you get something like this. And this is how the hash functions for LSH works for Euclidean distance. Okay, and up until about 5 years ago or so, everyone thought this was the right answer to how do we do a nearest neighbor search in high dimensions. And so but these graph-based methods work better. So that's what I'm having you do for your homework this year. Okay, this idea of building a hash function can work for a wider variety of distance functions, right? The graph-based stuff, I don't know if anyone's implemented it for Jacquard distance or not, right? Which it's not clear how that would work in the same way. So maybe it's possible, but the implementations don't exist as, at least the standard main implementations are for Euclidean and cosine. And so this is how the corresponding hash functions work. All right, any big picture questions on this? The main takeaways seem to be clear? Okay. All right, but this is kind of, I think, really cool stuff, how it works, and it allows you to kind of do some stuff really fast, but it has this overhead of randomness, basically, with 800 hash functions, I got this red curve that is not a threshold function. I want a threshold function, and it's easier to get certain similarities than to get ones near one boundary or the other, still have a high threshold. So it's you kind of see that it's not perfect, but it gives you an approximately right answer, right? And so you can try and maybe make sure you get everything that's above a threshold that you think might be similar, and then check all the distances exactly, might be what you want to do. Again, the graph-based methods work better, and they sometimes have failures where they don't give you the nearest neighbors, and it's not probabilistic. It's we don't really know why it doesn't work. So they sometimes will fail, and they won't know that they failed, and we won't be able to bound it, but they usually work better. Okay. I want to tell you about the last 20 minutes of this section and this lecture. I want to talk about an important class of distances that are really used for modeling, and some of these will show up in a lot of projects in the class. So distances for distributions. Okay. So one example of this is, think of the state of Utah, kind of, okay? And it's got some counties in it, like there's Salt Lake County, Summit County looks like this. Some counties here. Okay, Utah County is down there, and there's some, I don't know, if I'm drawing your county where you grew up or from really poorly, I'm sorry. I don't remember where all the counties are, but there are 29 counties. Okay, and I want to say that there's a season and there are some lightning strikes, or there's actually an array with that measuring these like neutrinos and stuff they have out in the desert someplace, but let's say lightning strikes. And I want to compare, this is one storm that moved through, and then I have another storm that has these red dots. Okay, and I want to compare the distribution of the two storms. Where are the lightning strikes? Okay, how would I compare these two distributions with each other? Are these two storms similar, or is there a third storm that was down in Grand County and all the lightning strikes were mostly down here? Which are the orange and the red ones more similar, or the orange and the purple ones? How do I measure this? I don't just have one point anymore. I now have a distribution of points. You could think of this as you collect two data sets. I want to say, are these two data sets similar to each other? Are they capturing the same distribution? Okay, how do I measure this distance between them? Okay, what do you guys think? How would I do it? Okay, yeah, I could take a mean of each of the distributions. Right, so this is the mean of the orange one, the mean of the red one, the mean of the purple one, and measure the distance between the means. So we'll see with clustering, this isn't a horrible idea, but I've lost a lot of information in doing this, right? This is definitely not a metric, because I could have two distributions that have the same means. One varies this way and one varies this way, and they're going to be very different. Right, so I could compute the means and measure the means, but I want to use all the information, not some summary statistics of the information. How would I use all the information? How would I even do that? Yep. Okay, so take the mean and record something like some vector that is relative to the mean. Now I want to so this, if I store the whole vector and I store the mean, this actually gives me a coordinate system for every point, and I do have all the information of the points, but how do I compare these to each other? Or maybe I just take the lengths or I still need to have a distance between them where I can say the orange and the red are somehow closer than the red and the purple. I want to be able to quantify that. All right, I will quickly go through some ways of how to do this. Okay, the first way is going to be I'm going to map to the county counts. Okay, so I'm going to have a red vector is a normalized counts. So it's going to be x in R M, so 29 counties. And so xi is going to be the number of strikes in county I divided by M. Okay, so I'm going to have two vectors that say how many are in this county, what fraction of them are in each of the counties. Okay, and then I can have two vectors, x for the red, and let's call this x, let's call y, x prime is the orange, and let's say x prime prime is the purple. And then I can just measure the Euclidean distance between them. In fact, all of these are in a space. We'll often call this as triangle m minus 1, or actually a superscript m minus 1. These are all vectors. So that it's a subset of RD such that each coordinate xj has to be in 0, 1 because it's a percentage, right? What fraction of the lightning strikes are in this county? And the sum over j, over these xj's, has to be exactly equals to 1. Okay, so there's a way of picturing this as a high-dimensional space, and I know it could be all in one county, all in another county, all in the third, and there's a triangle, and all the points need to live on this one-dimensional lower triangle in the positive orthant, right? All the values are between 0 and 1, and this must sum up to 1. So it becomes a d minus one-dimensional subspace, and then all the points live in the subspace, so I can measure the distance in this subspace. Okay. You typically don't use Euclidean distance for these. You would typically, for x prime in the most common distance would be called the Kullback-Leibler divergence, and they call it that instead of a distance. So the distance, the KL distance between A and B, often written as D of A parallel bar B for a little bit strange reasons, is going to be J equals 1 to M. That's the dimension that they're in. AJ times the natural log of AJ over BJ. Okay, this is the Kullback-Leibler divergence. This is an information theoretic distance. So I have two discrete distributions, A and B, and if I know what the distribution A is, how much information from an information theory perspective do I need to add to recover the distance B? That's what this captures. So if I have distributions and I'm thinking from an information, a signal processing point of view, this is kind of the right distance to use. You see, it's not symmetric. Okay, it's not symmetric. The distance from A to B is different from B to A, and kind of the double bar here kind of says you're going from A to B, not the other way, because that would put the BJs in front here and BJ over AJ, and so it gives a different distance here. So it's not a metric. This is common to use. I'll mention one more in this framework, the Hellinger. distance, the h between A and B. This one will be symmetric. It's 1 over square root 2 times j equals 1 to m of aj square root minus bj square root, this whole quantity squared and this quantity square rooted. It's kind of strange, huh? What this is doing is I've got points that lie on m minus 1, and I can kind of inflate them up to the unit circle, right? So I've taken A and I map it up here. This is kind of the square root of A. It pushes it out to here, and then it's the Euclidean distance between these guys. Square root of B, and then this is measuring this Euclidean distance between these two inflated points. That's, you can think of the Hellinger distance. This one also shows up as this one I think is a metric. I forget if it satisfies triangle inequality, but after you inflate it, it certainly does. So maybe it doesn't, but okay, so these are common ones to use when I have discrete distributions. Okay. Yes, thank you. Thank you. That is correct. That's not M, that is N, which is total number of strikes. Right. Okay. So this is, yeah, and so this is not an L2 normalizing, this is an L1 normalizing. They all have an L1 distance of 0, of 1. They all have they have an L1 norm of 1. Right? This is part of one's face of the L1 ball. Remember, the L2 ball is the sphere. The L1 ball looks like a diamond in 2D, but in 3D it has these faces, and it's this kind of this cross polytope that's called, and we only care about the one in the positive ortho. So all the values are positive. Yeah, thanks. Okay. What this did not capture, however, is that maybe these two counties are different. So I mapped it to counties, but these two counties are very next to each other, and these two counties are very far from each other. So so I'm missing the information by aggregating it onto the counties. So I haven't accounted for that yet. Okay, so this is, so if I have a discrete distribution like I have for like a like a bag of words representation of text, I can use these kind of Kolbach-Leibler or Hellinger, or there are other things that kind of NLP people have decided are the right way to do it. Okay, so let's. Nope, it didn't. Copy. Uh-oh. Now what do I do? Okay, well, okay, so let me say I don't have counties, and now I have three distributions. Distribution D, distribution D prime, and distribution D prime prime, and I want to know that these two are more similar than this one. How do I represent it? I could use the mean, but I've lost information. Maybe there's some stretching. So there are a couple of other things okay, so one way you could do is you could build a classifier between them, and whichever one you can classify how well you can classify them with as few mistakes as possible. This kind of works, but two things that are separable are all going to be completely separable. So this kind of limits things that are already separable. Like I can classify each of these from each other. A more common thing are the Wasserstein family of distances. Okay, and these are sometimes called the Earth mover distance. A version of this, the Wasserstein 1, is called the Earth mover distance. And so what this tries to do is it finds a matching. It finds a matching between the point set. Think I have piles of dirt is the red distribution, and holes is the purple distribution. And I want to move all the dirt from the piles into the holes so everything's flat. This was studied in like I think actually in like the era of like Napoleon. He's trying to move troops from one location on the map when he was trying to conquer Europe to another location on the map. And he said, I want to move my troops over here to attack this other zone. But I also want to send these other to defend this other region. And he ran into problems, right? He had too many regions. And so he's trying to figure out the best way to move his troops from one distribution of troops, the current situation, to another distribution of troops. And so they were studying these Wasserstein, or the Earth movers distances. And so what you do is you kind of find the best matching. So you find the best matching. We call this gamma, which is a map from D to D prime. And then the Wasserstein 1 distance between D and D prime is going to be the sum over kind of 1 over the number of things in the distribution, the sum over X in D, the distance from X to what it has matched to in the other distribution. So I'm basically taking the average length of all the matched line segments in between them, right? So this is the average of the length, and this is of the best matching. So in order to compute the distance, I have to find the best matching, the best movement of troops from one part of Europe to the other part of Europe. And I measure, say, Euclidean distance. Maybe Napoleon cared about the road network distance because going over the Alps was hard, right? Okay, and so this would be the Earth movers distance. This is a very popular thing to study nowadays, and it really captures well the difference between the distributions. It's a metric. It's kind of slow to calculate, okay? The time to calculate it, the run time just to compute the distance is something like n cubed, right? So because I have to solve for the best matching, and that's not so easy to do. In some settings, you can do it a little bit faster or approximately, and there's something called the Sinkhorn approximation, which speeds us up somewhat. But this is slow to compute, but it's a really informative distance between the distributions. We don't know how to do like an LSH function for this distribution. There are other distributions of distances, like there's one based on kernels that I'm not going to get to, where we can do LSH sort of things. But this is a really informative type of distance, and it works well for distributions in kind of any metric space. I can replace this distance by Euclidean distance by any sort of kind of metric space. Or I can take the sum of the squared distances and the square root of that, right? That would be the Wasserstein 2 distance, right? These are all metrics for kind of where, for values 1 up to infinity again. Okay. All right, so this kind of gives you another class of things to think about. What we'll see the rest of the semester is that how you model distance or similarity between things will kind of be needed to be used as the input to the problem. To run clustering algorithm, you need to decide what is the right distance. To do dimensionality reduction, then decide what is the right distance, or learn how to do the distance, right? To understand graphs, well, maybe you will build them using a similarity function. Okay, so this will kind of lay the foundation, and it's kind of important and there's a whole more variety of stuff beyond what I was able to cover. Okay, but we will have to stop here. And okay, and before you go, there are some example posters up front. Kind of look at these to get some more ideas about what sort of things you can work on and what I'll expect to see at the end of the semester.